last time we were looking at the fun and exciting towers of Hanoi, right? And what did we notice about the recursive structure? So if I wanted to solve the puzzle with, say, 5 disks, what did I have to do? Break out the ibuprofen, right? Right. So if you wanted to do it, say, for 5 disks, you would first move the top 4 disks out of the way, then move the fifth disk, and then move the other 4 back on top of it, right? So that was sort of the recursive solution, uh, was to think of it in that kind of 3-stage thing. Okay, now, last time we made a convention that I always do this backwards, which is, what do we call the biggest disk? Do we call that disk number 1 or disk number, say, 5, if there's 5 disks? Well, both conventions are certainly logical. I think last time we used disk number 1 to be the biggest disk. Yes? Okay. I'd like to go back in time and change that, and let's make disk number 1 actually the smallest disk. It doesn't really make a difference. It's all in just how we call things, okay? The only reason I want to make that change is because the program I wrote to do this, when I wrote it, I used n as the small, or 1 as the smallest disk, not the biggest disk. Okay, that was stupid on my part to let us go down the wrong or the other direction on Wednesday, but yeah, c'est la vie. Okay, so it's just a relabeling of the disks, not the end of the world. Now later, I'm going to rewrite my program for the other version of it, but for now, let's just go with it. Okay. All right. So what I've defined here is essentially this recursive function. So if you only have one disk to move, what do? You just move it, right? That's that. Okay. Um, and if you have more than one disk to move, let's say you have 5 disks to move, what are you going to do? Move 4 of them, then move the one, then move the 4 of them. Well, there's exactly a recursion right here. So this is basically the structure that we want to work with, right, is something like this. Okay. Now, if I run this program in Python, it won't work because move is not actually a valid Python command. Okay, and so I have a slightly different definition of it, which, let me get this out of the way here. And my slightly different definition here is, rather than actually moving, I'm just going to print the command or print text that says move whatever. Okay. And that's only because, like I said, move is not a valid Python. That's not a function. Okay. So I've got this slightly different version here. And that means I'm in the wrong directory. So let me fix that. And we'd be in Python. That's Hanoi.py. Okay. Okay, so this basically does exactly the same thing as the one before, except I've made it print the list of instructions to the terminal. And then in order to have it print and everything be formatted correctly the way I wanted, I had to put some of these kind of quotes and parentheses and some commas and a few other things. Don't worry about that. It just will make it print and look nice. But essentially, what's the structure here? If you only have one disk to move, what do? You just move it. And if you have more than one, you move all but the bottom one, then you move the bottom one, then you move all but the bottom one again. Right? That's literally it. Yes? Okay. So let's see this work, and also make sure that we get a list of instructions that actually works. Okay, so I'm going to call this by doing Hanoi of however many disks we have, the start peg, the end peg, and the temporary peg. And so let's just do it, say, for 3 disks, starting at A, ending at C, and going with B as our temporary peg. Okay, so the order I put this in is the game, right, is to get them from peg A to peg C, and who are we using as sort of our temporary dude? The one in the middle, peg B. Okay, so if I call this function, it should spit out a sequence of move instructions and double check that that sequence of move instructions actually is valid and solves it. And again, remember that I redefined it so that disk number 1 is now the smallest disk, not the largest disk. Do we have the correct number of instructions, first off? Yeah, okay. We saw last time, sort of experimentally, that with 3 disks, how many operations did it take to solve this? It took 7, and that is in fact the optimal number. This is that's a solved problem. Now, have we proved that it's an optimal? No, we have a lot of evidence for it in sort of a scientific sense, right? You guys all did it and nobody was able to beat 7. And so we would suspect then that 7 is in fact the minimum number of moves. But that doesn't actually prove it. However, it has been proved that this algorithm is in fact the optimal one, okay, for the problem. Okay, so do the moves work? Does everything check out? Yeah? Okay. And if I do this, let me call it for 4 instead of for 3. And how many moves should we expect to see there? Yeah, it's 15, right? And there they are. Okay, but structurally, what do you notice here, right? What's the sort of the secret sauce to this is what's the dude in the middle? Always the bottom disk. And you only move the bottom disk once. Everybody else, you move a whole bunch of times, right? So do you guys see kind of how this is sort of the onion unpeeling structure, sort of? Yeah? Okay. And of course, I could do this for any number of disks. So if I did this for 1,000 disks, well, let's see what happens, actually. Well, let me just do it for 100 and see what happens. It's still spitting them out, right? So get to it, gentlemen, right? How many disks are there actually in the kits, by the way? Is it like 10? Okay. So how many moves would it be to do all 10, by the way? What was the formula that we found for the number? Yeah, 2 to the n, then subtract 1. So 2 to the 10th is what? Yeah, 1024. And so to do this game with all 10 disks would take you 1,023 moves. Now here, what did I put in? 2 to the 100th, right? Um, well, let's just see what number that is. Wolfram Alpha, 2 to the power of 100 is, it's basically something times 10 to the 30th. Yes, good point. Well, they're there. Yeah, it's just that they go by so fast. So every now and then when you see something that kind of pops, that's where a 2-digit number is happening. Um, yeah, but like you end up moving disk number 1, the smallest disk, just a ludicrous number of times, right? And the further down in the stack you go, the fewer times you have to move that disk. But where the ultimate end of it is the biggest disk, which you only actually move once, right? Um, yeah, so my computer probably is going to catch fire here at some point, but here we go. Okay, so you get the idea that this is going to take a while, and in fact, let's do it. We did it for 100. Let's just see how fast it spits out the instructions for 10, almost instantaneously, right? And there they are, all 1,023 of them. Okay, so we know that this is in fact an optimal algorithm and how many steps it takes, and we've essentially cracked it, right? Um, so this puzzle, right? Any anytime you play with a puzzle or a game or whatever, what could you do? Could we change the rules? Yeah, and then ask what happens if we change the rules? How could we change the game that's sort of like this but not identical to this? What can we do? Any just random idea? Right now it's Buffalo medium. Okay, let's make it Nashville hot or maybe blazing if you want. No, because the difficulty of a math problem is on the same scale as the wing sauces at B Dubs. Has anybody actually done the blazing challenge, by the way, just out of curiosity? Yeah. Have you done it with the bone-in wings or the boneless wings? Okay, I don't like bones in my food. Like, I feel like that should be removed in a factory someplace. Huh? Exactly, right? You just have a knife and a fork and off you go. It's great. I did the ghost pepper wings once, or twice actually, at B Dubs. They were so spicy I started hallucinating. It was pretty, yeah. I mean, it wasn't like full on like mushrooms or acid trip kind of hallucination, not that I'd know, but it was definitely an altered state of consciousness. It was interesting. So anyway, okay, so yeah, how can we modify the game a little bit to be, different? Well, lots of things we could do. What about if we had a fourth peg? Okay, well, do you think that they could speed up the algorithm a little bit potentially? Yeah. Okay. So if we had an extra peg, sort of one extra peg, you can't do this with two pegs. You have to have the third peg. But if you have a fourth or further, maybe you could speed the algorithm up a little bit. That's sort of an interesting question. The other variation of this I've seen, and so let's go to the bastion of all knowledge of Western civilization, namely Wikipedia. Because there's several variations that are listed on the Wikipedia page, which are kind of interest. One of them is that you only can move to an adjacent peg, so you can't ever move uh, directly two pegs over. Okay, so that changes it. Another one is where instead of the pegs being in a line, they're arranged around a circle, and you can only move clockwise or counterclockwise either way. Okay, so that's kind of interesting. Um, Four pegs, and actually the four peg problem, the solution to it was not known to be optimal until 2014. Right. So this was still a very much an open problem in computer science as to whether or not the sort of obvious algorithm was in fact optimal. Um, and that maybe no shows that one of the things that's interesting about some of these problems in computer science and in other branches of mathematics is they're very easy to state, they're very hard to answer. So anyway, okay, so the four um, pegs. Let's see. There's also this one, which so this is sort of a specific case of the puzzle where you have exactly four disks. You're not trying to be general, okay? And this was given in a competition, basically a um, math and logic puzzles competition in France in 1988, and it was given to third through sixth graders. Okay, and this version is you, instead of starting with one stack of disks, you actually start with two. And the disks are colored so that you have white disks and black disks, and they start in the initial configuration where both stacks are alternating. And the goal is to rearrange them so that you have all the black disks stacked on one peg, all the white ones on the other, and of course you need a third peg to do this. Okay, what's the one extra rule that we need to consider in this particular case? So how many different disks of a given size are there? There's two this time, right? Are we allowed to stack a big disk on top of a smaller disk? No. But what about stacking two disks of the same size on top of each other? Should that be permitted? Yeah, otherwise you can't do it. Okay. And this solving it for four disks is not all that hard to do. It requires a bit of thought. Okay, but where this gets really hard is trying to solve it in a general case. That's much, much more difficult. I foolishly gave this as a problem to a previous CS-101 class, and well, let's just say it's a good thing I'm still alive, because I thought, like, had Yik Yak been around when I taught that particular class, yeah, it would not have been pretty. Also, speaking of Yik Yak, you're all fired, because you know what there wasn't a single instance of on Wednesday? Appreciation for us finishing early so you guys could get in line quickly for the chicken tendies. Not a single one of you. Okay, so you're all on my hit list. Yeah, so you can expect a couple of red turtle shells on your first exam. Okay, coming for you. Or actually, you know what I'll do is I'll lightning you and then red turtle shell you. Huh? Yeah, it is. It is kind of red. So anyway, yeah. So this particular version of it was given only with four of each color. Okay, and that solution's not horrible to come up with, but it does take a little bit of work. Okay, so yeah, so there's lots of interesting variations to this puzzle. You guys could think of others maybe. And yeah, okay, but we've essentially cracked this in the sense that um, we figured out not just how to solve it for a specific number of disks, but how to generate the formula for any number of disks, right, with our recursive function, okay? Okay, good. So what I want to do next is let's sort of return to a couple of other recursive-like functions that we could consider. And in particular, I'd like to consider the factorial function again. Okay, what was the factorial defined as? So 5 factorial meant to do what? 5 times 4 times 3 times 2 times 1, okay? And what was the recursive way of thinking of that? What's 5 factorial? 5 times whatever 4 factorial is, okay? So here I've defined this as a Python function, okay? Factorial of n, well, if n is 1 or smaller, what's the factorial of, say, 0 or 1? Those are both defined to be 1, okay? And then if the number is bigger than 1, so like 2 factorial, what is that? It's 2 times whatever 1 factorial is. What's 1 factorial? 1. And so 2 times 1 is 2, and we're done, okay? It's critical in any recursion that you have to have a base case, right? The recursion cannot go on forever. There has to be a stop at some point, okay? And so here I've defined this recursive function. I call it fact. Um, basically, it's the factorial function, right? And let's see that it works. Okay, so if I plug in factorial of or fact of 5, what should I get? I should get 120. And in fact, I can do, there's the first however many of them, first 10. Okay, so 1, 2, 6, 24, 120, 720, and so on. And as you can see, these numbers grow pretty quickly. Okay. In particular, what would happen if I did, say, for I in range to do the first 100 of them? All right, so that got kind of line wrapped, so let me kind of do this, right? So what happens to these numbers? They get really big really, really quickly, right? To the point now where 100 factorial is this gigantic number, and actually, that's interesting. Yeah, it gets really big really quickly. Yes. And in fact, this is sort of interesting. Notice what 99 factorial is in relation to 100 factorial. Well, 100 factorial should just be 100 times 99 factorial. Look at the two sets of digits at the bottom. They're the same, except at the end you have two extra zeros, right? That makes sense. Okay. So yeah, the factorial function grows really, really, really quickly. And if I try and call this for a ridiculous number, okay, what's it going to do? It threw an error here. It basically said maximum recursion depth exceeded, right? So going up to 1,000, I can't do that on this computer. Let's see if I could get to 500. Yeah, I can do 500. Let's see, 600. Yep. 700. Okay. 800. Good. 900. Good. Let's try 999. Nope. Can't do that. 960. 70. 80. 90. 1, 2, 3, 4, 5, 6. Yeah, okay. So it looks like I can go a maximum recursion depth of 998. There's got to be a good reason for that particular number. I'll do some investigating to figure that out. But, you know, I mean, if ever there was an opportunity for a Yo Mama joke about Liam's mom, it's right here, right? Okay. So, yeah, huge number. Now, I should also mention then that, this is not the optimal way to actually do this, to define it. We don't have to define things recursively. It's just that often that's the easiest way to define it. So the next example that we'll look at, I think will show you guys that recursive definitions are easy to write down, but sometimes computationally extremely inefficient. But then there are other ways that maybe you can come up with how to program something that are harder to think about, but run faster, right? And that's sort of the trade-off that you're always going to have. Okay, good. So factorials grow quickly. Yes? All right. Has anybody else seen any other kind of recursive recursively defined function or sequence, perhaps? Has anybody ever heard of the Fibonacci sequence? Yeah, what's the Fibonacci sequence? Really famous. Uh, Almost. It's the sum of the two previous numbers. Okay, so the Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, and so on. Okay, how did I generate this set of numbers? Well, the first two numbers I just have to pick, 1 and 1. Okay, and then the next number is the sum of the previous two. So 2 is 1 plus 1, 3 is 1 plus 2, 5 is 2 plus 3, and so on. Okay, that makes sense, the idea? Okay, so let's program that and see what this looks like. Okay, so let me make a new file, and I'll call this def Fibonacci of n. And let me go ahead and save this real quick. Okay, so the initial definition is if the number coming in, oh, and I should have saved this as a Python file, my bad. There we go. Why is this not tabbing? Oh, that's why. There we go. Okay. So if the number is 1, or sorry, not less than or equal to 1, I want less than or equal to 2. If the input number is 1 or 2, that means it's less than or equal to 2. The answer is just 1, finished. Okay. Otherwise, I'm going to return the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. Okay, so for example, what is the fifth Fibonacci number? It'd be whatever the fourth one plus the third one is. What's the fourth one? The third plus the second. What's the third one? The second plus the first, right? And so this goes down. And then what are the first two? 1 and 1. Okay, so got this perfectly good recursive definition. Let me save this and let's load it into Python. And let's see, you here. Need to quit. And the computer is about to crash. There we go. Where? So I just didn't use the installer. So if you just go to the Python website, there's an installer, and it installs it to like use your local bin or someplace, which is, you don't have to think about that. But then it also adds it to your environment path, so I can do Python from anywhere. I can do it here in the console. If I pop open VS Code, I can do it there, right? Um, yeah. Um, okay, anyway, so I've got that, and then let's import it. So from Fibonacci to import everything. And then I made my Fibonacci function, Fibonacci of whatever. Okay, so Fibonacci of 5, the fifth Fibonacci number is 5. And in fact, let's do another loop. Okay, so there's the first 100 of them. But you'll notice it's not actually done doing the computation, right? And in fact, the bigger that the number is, the longer it takes to compute it. Now, there's a couple of reasons why that's happening. One is the recursion depth here is much larger. Okay, the other is that we've actually been really inefficient in the way that I wrote that code. It's very simple code, but it's inefficient code. Because if I want to know what, for example, the 10th Fibonacci number is, I need to compute the ninth and the eighth. But in order to compute the ninth, I already need to compute the eighth, right? So I end up computing each number more than once. Is that a good thing? No, that's extremely inefficient. Okay. So what would be better for me to do, and this would complicate the programming but simplify the execution time, okay, is to keep track of all of the numbers that I've already computed. And if the number is one that's already in that list, just pull it out of the list. I don't have to recompute it. Okay. Doing that is called memoization, by the way. Um, and the other way I could do this is not think about this recursively, but rather think about it iteratively. And combining the two together is sort of the optimal. One other thing I'll point out about the Fibonacci's, where did they come from? Does anybody happen to know sort of the origin of why Leonardo of Pisa, the guy who we now call Fibonacci, why he was kind of interested in this math that led him to discover this sequence? I'll give you a hint. It involves lots of sex. That got y'all's attention, okay? But it was rabbits having sex, not humans. Um, and in particular, right, what's the joke we have about rabbits? Yeah, they breed very, very quickly, right? And so he started with sort of the puzzle. Okay, suppose you have one pair of breeding age rabbits, and they do their thing, and mama rabbit's going to have two baby rabbits, one male, one female. Okay, those baby rabbits take a year to mature before they're of breeding age. During that time when they're maturing, the original mama and daddy rabbit can still get busy and gestate yet another set of rabbits. Okay, so the question is, how many sets of rabbits are there at each year? Let's just assume it takes 1 year to gestate a rabbit baby, and also 1 year to reach for a baby rabbit to reach breeding age. Okay, just suppose. Further, let's suppose that these are rabbits from Arkansas, which means that they have no problem with some inbreeding. Okay, um, yeah. Both sides of my family are from Arkansas, so I feel like I can, make that joke. I mean, it could be worse, right? It could be like the lineage of the current, royalty in Europe, right? Which is all super inbred. Anyway, um, okay, so that's how he was sort of thinking about this puzzle, and anyway, ended up with this sequence of numbers. Now, this sequence of numbers is really interesting for reasons that have nothing to do with breeding rabbits. Has anybody run into this sequence in other contexts? Had any of you ever heard about this sequence before you walked in the room today? Who had heard of the Fibonacci's before you walked in the room today? Under what context had you heard of them? Just in math class. Okay, well. And the Fibonacci's came up? Okay, I'm going to have to go find that episode. Okay, all right, that's interesting. So I did not know that. Now that said, there are lots and lots of really awesome math jokes and mathematically related things in The Simpsons and also in Futurama. Uh, because you wouldn't, this might surprise you. A number of the writers and stuff were like actually math majors in school, and so there's math humor all over the place. You just have to know where to look. Probably the greatest example of it is, how many of you guys have seen the movie Bender's Big Score? Um, so this is the one where Professor Farnsworth invents the brain switching machine. So if two people sit down, like in the machine, then it would switch our brains. So my brain would be in the other person's body and vice versa, but you can't switch back. And so then things get all mixed up because like Farnsworth's brain is in Bender's body, and the mop bucket, it has somebody's like a robot's brain in it and whatnot. Um, and then one of the characters like, is it possible using two or more temporary bodies to get everybody back in there? And so then it's, like, I don't know, we may have to use math. So then they call in the Harlem Globetrotters, right? Because those are the geniuses in the show, to help them solve the problem. Yeah, anyway. Um, so this sequence of numbers actually comes up quite frequently in places you wouldn't expect it, nature even. So if you count like the flower petals around a flower going around the ring, they expand in the Fibonacci sequence, which is kind of interesting and surprising. The other thing that's really interesting about them is if you take any Fibonacci number and you divide it by the previous Fibonacci number. Okay, so for example, let me just pick one where it's pretty obvious what's going to happen. Let's take this pair right here, 102,333, or sorry, 102,334,155, and the one following it, 165580141. If I divide this one, the 16 blah blah blah, by 10 blah blah blah, what am I going to get? Like 1.6 something or other. Okay. And it turns out that if you go further down in the sequence and do this division, that ratio converges to 1.618 blah, 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 which, does anybody happen to recognize that number? Here's the exact value of it, by the way. It's 1 plus root 5 all over 2. Anybody recognize that number? We call this phi. It's the golden ratio. Have you guys seen that in math class? You guys disappoint me every day. That's true. That's true. That's true. Although, to be fair, the last 3 years have kind of sucked. I mean, especially sucked because there was this whole virus thing that showed up, and then the lockdown. And how many of you guys, even last year, were in virtual school? Yeah. What about the year before? Yeah. And you guys all remember the lockdown, right? So, anyway, um, yeah, if I weren't young, like if I were close to retirement and then the pandemic happened, I would just be like, you know what, forget it, I'm done. I'm not teaching this way. Um, okay, anyway, so yeah, these Fibonacci's, right, are very interesting mathematically for a whole host of reasons. Okay, so but as you saw, this recursive way of programming them for large values was very, very slow, right? So let's do it a different way that will be much faster. Okay, and I'm going to do it this way. So I'm going to define a second function. I'll call it Fibonacci iterative, and it will also take a number. Oh, and I can't have a dash in a function name. Oops. So I'll do this. Okay, and I'm going to define this one in terms of a loop. Well, first off, um, I'll go ahead and put in this catch case. Well, actually, you know what? No, I don't want to do that. Okay, so what I'm going to do is I'm going to define and then I want to do and then I want to return the number y. oops. All right, let me just make sure I've got everything I need there, and I'm going to have to quit and then reopen it from, what did I call this, Fibonacci to import star. Okay, and I want to do Fibonacci iterative, and then let's just test this with, okay, 5, 6. Okay, so I've got an off by 1 error. Let me change this to 0. Oops. Okay, there we go. Okay, and there we go. There's our sequence 1, 1, 2, 3, 5, 8, and so on. Okay, but in particular, let me turn this thing loose on the previous sequence where I had it trying to do 100 of these, and we saw it was kind of croaking. And there, bam, it did all 100 of them that quickly. Okay, so what am I doing here? I'm essentially building up the list, but I'm doing it iteratively. And in doing so, I don't end up having to compute the same things multiple times or as many multiple times. Right now, I still am computing it multiple times. Um, but yeah, it spit out the first 100 and no big deal. There they are. Okay, it's kind of interesting how much faster that was, right? Um, and um, what I could also do, actually, just for giggles, is let me do this, but also I'm going to print. Um, actually, there we go. Okay, so what I've done here is I've printed. I could have skipped printing the numbers, but I printed each number divided by the previous one. Okay, and what do we notice? Yeah, you see that 1.618 blah 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 that sequence is converging, or the ratios are converging to, and that's this number, by the way, okay, that I mentioned. Okay, so how could we improve the efficiency even more? Well, we could do, like I said, called memoization, where if I have already computed the 10th Fibonacci number, do I need to compute it again? No, I should put it in a list and store that list and then access like that data as I go, and that would speed this up even more. Now, for the first 100, right, with my little program here, it wasn't really all that horrible. The iterative one could do it almost instantaneously, but it's still super inefficient. Um, yeah, okay. Um, right. So, I think that's probably about where I wanted to finish. Questions, preguntas, fraggens? Just to put this on the horizon, our first exam will be the week after fall break. Not next week, but the week after. Um, and we'll talk more about that next week. So, all right. Well, I guess we can quit a little early. Have a good day.